Alright, so let me give you some background for this lab. And this is stuff that we've actually already covered, so it's going to be a nice review for you. Alright, oxidation reduction reactions involve a transfer of electrons. In a spontaneous redox reaction, electrons flow from the reactant that is oxidized to the reactant that is reduced. If the two half reactions are separated by a wire, this flow of electrons, instead of occurring at the surface of the metal, occurs through the external wire, and an electric current is generated. This is called a voltaic cell or a galvanic cell, and is exactly how a battery works. Batteries, like the ones found in a flashlight or calculator, contain oxidizing and reducing substances. As the electrons are transferred, they are used to provide the voltage necessary to power the flashlight or calculator. A good analogy for the flow of electrons is the flow of water. Water flows spontaneously downhill. Dams and water wheels are examples of ways that the energy of flowing water is tapped to generate power. Sometimes we want water to flow uphill. In this case, we need to supply energy in the form of a pump to make this happen, and that's what we're doing in this lab. In order for a redox reaction to serve as a source of power, the reaction must be spontaneous. What if the reaction isn't spontaneous? In this case, we can use electricity to make the reaction occur. That's our pump. An electrolytic cell is a device that uses electricity to drive a non-spontaneous redox reaction. For example, water can be separated into hydrogen and oxygen, a non-spontaneous reaction using electricity. Hint, that's something we're going to do today. The reduction and oxidation reactions that occur in an electrolytic cell are those that have the least negative cell potential. Okay? In short, the field of electrochemistry has two important applications: the use of spontaneous redox reactions to generate electricity, and the use of electricity to force non-spontaneous redox reactions to occur. So in this pre-lab, we are going to look at our first example of an electrolysis reaction, and I'm going to walk you through it, and then we're going to actually observe what happens. So the first reaction we're going to have some sodium sulfate dissolved in water. Okay? And what you will be given on the AP and on quizzes and tests is you'll be given these standard reduction potentials, and you'll need to use those in order to determine what is actually happening. So let's look at that. So what are the potential reactants? What could be reactants? Well, if I'm dissolving sodium sulfate in water, that means that one reactant could simply be water, or it could be sodium ions. No, it's not just Na, it's got to be Na+, because sodium sulfate, when it dissolves in water, it becomes sodium ions and sulfate ions. So those are your three potential reactants. So I'm going to figure out the reduction reactions that could occur with these three reactants and the oxidation reactions that could occur. Okay? So let's first look at potential reduction reactions. Well, there are two of them. The first one, notice I had sodium ions. So I could have the reduction reaction of sodium ions becoming solid atomic sodium. Okay? And when I look back at the chart, the cell potential for that is negative 2.714. The other reduction reaction I could have is with water. So water gaining 2 electrons to become hydrogen gas and hydroxide. The cell potential for that is negative 0.828. So the one that's going to occur, the reduction reaction that's going to occur, is the one that's the least negative, which means water is going to be reduced. Okay? So we're going to do the exact same thing, but now for oxidation. All right? So one potential oxidation reaction is going to be water. So if you look at your reduction reactions that are given on that table, okay, and I'm actually going to have us go back and look at that right now. If you look, water, because this is going to be an oxidation reaction, I'm going to have to flip any of these reactions that I want. Well, I want water to be a reactant, and I need the electrons to be on the other side. That's why I'm flipping it. So if you look, the second reaction there, water becoming oxygen and hydrogen ions and releasing electrons, that would be a perfect oxidation reaction, right? Because water is still a reactant. It has to be a reactant. Now the other one, if you look, sulfate needs to be oxidized. Well, if you look at this, in this one example, and not in what you're going to do in the lab, but in this example, sulfate will not be oxidized or reduced. Okay, so normally you would have to compare the values like what we did for reduction, but in this case, we're only going to have water being oxidized. It's an exception. You won't have that happen in your lab. So it's just going to be water decomposing into oxygen gas, hydrogen ions, and electrons. The cell potential, remember, I have to take the negative of whatever the reduction was. So it's going to be negative 1.23, okay? And that's the one that's going to occur. Normally, in what you'll have two different potential reactions and then compare it like what you just did up above. So in this video, I'm going to show you the first example of an electrolysis reaction. So the first thing I'm going to do is I'm going to take my Petri dish and I'm going to pour some distilled water in it. Okay. Make sure it's totally full. Okay. And then I'm going to add just a little bit of sodium sulfate into it. Keep in mind, as I had already reviewed, your potential reactants are going to be water, sodium ions, and sulfate ions. Okay, and as we noted, or as we will note, it's interesting. Most of the time you can assume those will be your three reactants and that all of them have the potential to react, either to be oxidized or reduced. But for some reason, which is beyond the scope of this class, sulfate does not. So really, your two solutions, your two potential reactants are going to be water and sodium ions. But let's make sure that is a correct assumption. So I've got my battery here. I'm going to connect one alligator clip there and one alligator clip there. Now I'm going to connect them to my pencils, okay, to the graphite of the pencils, because while we assume it's just metallic compounds that as solids conduct electricity, graphite, which has covalent network bonding, it's all covalent bonds, that's why diamond is so strong, it also conducts electricity. So it's attached there, and then the black one needs to be attached to the other pencil. Now you'll be doing this in the lab with two new solutions and trying to figure out what's going on. All right? The other solution I need is my universal indicator. Okay? So I'm going to grab a pipette. I'm going to add just a couple of drops of my universal indicator. Okay? And then I am going to take my spatula and I'm going to stir it. Okay, so it's kind of bluish in color right now. So now if I take the two electrodes, make sure they're not touching, and allow them to touch the solution, what you can see is happening is you've got, look at that purple one, you've got bubbles forming on that one, okay, and it's turning purple. For the other one, bubbles are forming as well, but now it's turning pink. So you can even make some cool designs with it. Pretty cool, huh? Okay, so you're going to be doing this in lab with different solutions. You're going to be causing the electrolysis of different solutions and having to figure out a solution, what is actually reacting. Okay? So now that you've actually seen the reaction, we need to link our equations with our observations. So we know that oxidation occurs at the anode, and what we observed was that it turned pink. Well, why did it turn pink? Well, it turned pink because water was being oxidized and it produced hydrogen ions. Hydrogen ions are acidic, so it's going to release H+, which is going to cause it to turn pink because it's acidic. Notice also it released bubbles, and that's in the form of oxygen. At the cathode, reduction occurred and it turned purple. And we know that happened because if you look at the reduction reaction, hydroxide ions were produced. That's what caused it to turn purple. And then also we saw bubbles, and that's because there was hydrogen gas. So what's the overall reaction that occurred? Well, remember, I have to take these two half reactions and I have to add them together. Notice I've got 4 electrons for the top, 2 on the bottom, so I'm going to multiply the bottom by 2. And so when I add these up, what I get is 6 waters producing oxygen, 2 moles of hydrogen gas, 4 moles of hydroxide ions, and 4 moles of hydrogen ions. Now, keep in mind, hydroxide and hydrogen ions, when they combine together, OH- and H+ produce H2O. So the 4 OH- and the 4 H+ actually produce 4 H2Os. So I can simplify this, get rid of the 4 H2Os on my product side, and then I would simply have 2 waters on my reactant side. And so 2 waters decompose to form oxygen gas and 2 moles of hydrogen gas. And that is what we call the electrolysis of water. So you actually got to see that and see that hydroxide ions and hydrogen ions are produced because you're able to see the color with universal indicator.